Let's look at what the real data that breaks us out of just what are stories and really takes us into the hardcore evidence. And what we're looking at right now is a snapshot. It's a snapshot of what the Earth's climate was like over the last about the last 20,000 years. And there's some very interesting things you notice, like the fact that when this period of the Younger Dryas ended, just after the gray area, what we would consider kind of a violent climate over the last couple thousand years has been in so many ways stable if you compare it to what these events that occur in our past. And that's what we're going to talk about. If you say to yourself, well, I don't really believe in the stories of these big floods that occur in the past and these things that were talked about in these stories because they're too incredible. They're too far beyond what I can imagine would be possible to happen. But when you look at this and you see that we had plunges in temperatures and rises in temperatures so dramatic that in the course of someone's lifetime, you could see the entire transition of planet Earth into a different kind of ecological zone. A time of thrusting us into some of the coldest temperatures we've ever experienced here, in the last 100,000 years, to then thrusting us into rapid warming. And we have to remember what comes along with those types of events. That represents climate. And this represents telling us where were these temperatures. And those temperatures are going to mimic what kinds of storms existed and what kind of environment was present on the Earth at that time. And 12,800 years ago, this first plunge, right? You get this first plunge of temperatures that go down to almost the coldest they've been in the last 20,000 years. Right at that one moment, and then you get a slight rebound you get a less than 1,000-year period. And all of a sudden you get this complete other end of the spectrum rise in temperatures where you go 3 times what it was before in a very, very, very short amount of time.
When we look at this graph, basically what we're seeing here is that coming out of the Ice Age, you can kind of see that we're coming up here, and then we have this first massive spike of warming, and then it seesaws back down into this full glacial cold. This is called, this period between these two green arrows is called the Younger Dryas, which is named after a polar wildflower that had disappeared in northern Europe and then suddenly came back again. It only grows in polar environments, Dryas octopetala. So the Younger Dryas, compared, because there was an older Dryas too, but it lasted, now the dates are placing it from roughly 12,900 years ago, give or take a few decades, to 11,600 years ago. So this spike of warming right here is 11,600 years. Now if we look at the next one here, this graph basically goes to a different realm of evidence, and what this shows is the average, the rate of sea level rise, you see. Now, oceanographers and marine geologists have been studying, there's a number of different ways they can correlate this information. They can look at actual evidence of submerged shorelines, right? They can look at changes in the flora and the fauna that have lived in the oceans. They can look at coral reefs. There's a lot of different things that they can pull together to see how rapidly sea levels rose at the end of the last ice age. And again, a generation or two ago, the assumption was that there was a smooth continuum of rise that took tens of thousands of years, right, to get us from minus 400 feet up to what we are now at the present level. What this graph shows is that there were two massive spikes of meltwater introduced into the oceans, into the global oceans at the end of the last ice age. And you can see the first spike, called meltwater pulse 1A, is the biggest, followed by another one, meltwater pulse 1B. If we go back to this graph right here, those two spikes of glacial meltwater and sea level rise coincide with this warming spike and that warming spike. And you can see how this warming spike seems to be the most intense, followed by this one, and we see that meltwater pulse 1A is the biggest. So what this is showing is that the rise in sea level was not as smooth. It was like whoomp, and then whoomp again. If we look here at the image, you know, I've got a measuring tape here. You're going to see the wavelength is about 3 inches. The amplitude, the vertical height of these things is about 3/4 of an inch. It's been carried along, swept along in this water that was over this floodplain, which was 2 feet deep. Carried along, and as the water declined, it deposited this sand and then rippled it as the final stages. So now, just so you've got this by comparison, we'll go to this. This is what Graham was just talking about, Camas Prairie. And what you see here is there's ranches out there, and you've got this 10-mile long field of these gigantic ripples. And if you look up in the upper left-hand corner of the screen, you can see some of these ripples. They're, like Graham said, they're 100 to 300 feet in wavelength, and they're up to 50 feet in amplitude. And the water that flowed through here that deposited this was over 1,000 feet deep.
This is fractal. You get it.
Exactly.
You get it in the small scale. In the first image, Randall showed the same phenomenon there with a flood just 2 feet deep, and then we come to this humongous testimony to what happened 12,800 years ago. And it's easy to drive through it and not really figure what you're driving through, but once you look at it and realize what happened, it really dilates the imagination.
Can understand what this is because we can see it on any beach. We can see how water flows receding across a sandy medium will produce ripples. But here, they're on this unbelievable scale where they're hundreds of feet long and 50 feet high, where they dwarf houses, and they're lying all across. And what that tells us is that a huge water flow went across this plain and did this.
The way to visualize this is to, again, begin to think a tsunami. You have to think tsunami because tsunami is the closest scale of water flow that we've experienced in modern times. No river flood has even approached this. But even there, you got to picture the tsunamis that we've experienced in the last decade and a half, and in Indonesia and Japan. When they made landfall, those tsunamis were roughly between 20 and 50 feet, depending on where you were relative to the oncoming wave and how far distant you were from it. Here what you have to visualize is a tsunami sweeping over the land that's over 1,000 feet deep. That's what happened here. And we know that because we can trace the high water marks on the hillsides are clearly left. The high water marks are clearly etched into the hillsides. So we now know, based upon the study of the ripples, and the water here was moving down. It's filling this basin. It's rushing in a great tsunami from the north of fresh water, meltwater, coming off the ice sheet. And it's sweeping down over this land at probably 200 or 300 million cubic feet per second, which is an inconceivable amount. It's many times in excess of every river flowing on Earth, flowing today all at once. It's beyond that many times, 10 or 20 times beyond that. One of these flood flows here is 3 orders of magnitude greater than the largest measured modern flood. In other words, over 1,000 times greater. In terms of peak discharge or volume, you would have to scale up at least 1,000 times greater than any modern measured flood to get to the smallest, really, of these flows here. Because this is just one place, one locale on 5 states where you can trace literally an ocean of fresh water sweeping across the entire Pacific Northwest. You can see in this here that you've actually got 3 massive currents converging here. Do you see that over here on the right, you've got a massive current coming in that would be from the west. And then we would be standing looking down current. Of course, the drone I'm guessing here is about 200 feet in elevation. So the top of the water was another 800 to 900 feet above this perspective right here. And it's moving very, very fast. And it's sweeping down into a river valley that's down in those mountains you see in the distance. And from there it's being carried down and joining up other equally as large floods coming in from other valleys. And all of this is happening at once, and it's covering 5 states basically. And that's just one region that's being affected by this sudden catastrophic melting of the ice sheets.
We are dealing with the largest flood that ever occurred on Earth. It's as simple as that. It
The
happened here
largest?
in North America, and it happened 12,800 years ago, and its story has yet to be fully told.
What's further interesting is when we look at this graph. This is the late Pleistocene mortality graph, and each square represents a fossil specimen of an extinct mammal. You know, could be a woolly mammoth, could be a giant ground sloth, could be a saber-toothed cat, could be the giant cave bear. Roughly 120 species of mega mammals that lived during the Ice Age went extinct, right, at the end of the Ice Age. And basically, what this graph is showing us here is that, you probably can't read this here, so I'll interpret it for you. If you go back to here, the left side represents 50,000 years ago. And here, where the cursor is, that's 40,000 years, 30,000, 20,000. And you see that as we're going along here, each one of these squares represents the finding of a fossil of an extinct mammal in the fossil record. What we see from this graph is that when we get to between 11 and 13,000 years ago, there's a massive spike of mortality. Shoots through the roof. This demise of these animals
directly coincides
with this right here. Directly. the realization came upon researchers in the early 70s that the glacial ice, this huge amount of glacial ice, had melted so fast that they couldn't account for the energy source necessary to melt the ice that fast. And they struggled with it. There was a series of articles that basically were in the scientific literature from 1973 to 1976. And then I pretty much, after that, you don't see much about it anymore, because if you read the tone of the articles towards the end of this period, they're almost sort of giving up in desperation, saying, well, maybe there's an error in our data somewhere. You know, maybe this, they essentially just gave up on the problem. Okay, so what happened even between the early 70s, when this, what they referred to as the energy paradox, first became apparent, and now is that the problem has become even more acute. Because in the 1970s, they were struggling with an 8,000 or 10,000 year melt-off period. Now, with the data we have in hand now, suggests that the melt-off period did not exceed 3,000 or 4,000 years. And the second thing is, if you remember, I've shown you this graph now several times of the rates at which meltwater entered the ocean, and you could see that it was not uniform between that 3,000 and 4,000 year period. There was actually two extreme spikes of meltwater that flowed into the ocean, and which in a sense makes the whole problem that was originally posed back in the early 70s even more intractable. Because if they were not able to provide a source of energy to melt the ice within 10,000 years, how do you essentially explain the melting of the ice over two very short intervals, which may have lasted no more than a few centuries each, maybe even less than that? Is that getting rid of this mass of ice requires an extraordinary amount of heat energy. Okay, so where does such a source of heat energy come from? Well, one reason why the scientists of the 70s essentially gave up and assumed the problem was intractable was any source of energy that they were trying to invoke to explain the rapid melting. All of those explanations were all Earth-based. They were all terrestrial.
In a remote area of northwest Greenland, an international team of scientists has made a stunning discovery. Buried beneath nearly a kilometer of ice, it's an impact crater, 300 meters deep, 31 kilometers wide, much bigger than Washington, D.C., even bigger than Paris, and it's probably one of the youngest large impact craters on Earth. The scientists confirmed the telltale bowl shape and central peaks beneath Hiawatha Glacier. They also found that the oldest ice in this crater was actually fairly young by Greenland standards and had experienced a great disturbance in its flow toward the end of the last ice age. The team then visited the area on foot, and in sediments deposited by a river draining out of the glacier, they found grains of the mineral quartz that showed signs of being physically shocked in a massive impact. Models suggest the asteroid was more than a kilometer wide. The Hiawatha crater is one of the 25 largest known impact craters on Earth, and the first found under any of our planet's ice sheets. Impact could have also occurred when ice already covered Greenland, and it would have instantly vaporized billions of tons of ice and rerouted the flow of ice and water into the ocean. Whenever the impact happened, life on Earth at the time would have been profoundly affected.